All right, so I was originally intending to show this when we do industrial components next week or the next session, but this is something you're going to have your hands on today, so it's nice to know on a wire there are two regions to be concerned with. One is the insulator, that's like the plastic or rubber outside, and it's low resistance. It's not meant to conduct electricity, it's meant to stop electricity from flowing. And then the conductor is on the inside, that's copper or aluminum or whatever. And it can be either stranded, which is really frayed for flexibility, and then solid core, which is just a solid piece of copper. Most of what we're going to see today is stranded wire. Back in the day, when lots of this stuff was first being figured out, like building the tools, they had a system, a device just for measuring voltage. That was a voltmeter, and then there's a separate one for doing amperage, current. That was an ammeter, and then you had ohm meters for measuring resistance, like on a resistor. And that has been combined into a single device, a multi-device. Multimeter is what we have here sitting in front of you. And on that multimeter device, it's basically the go-to device for figuring out what's happening in a circuit. On that, the way you figure it out is with these probes or leads. Anytime you have wires sticking out of something, it can be called a lead. So you've got a red lead, which is the high side. That would measure like the plus side of a battery, and then the minus side of a battery would be measured with the black or low or common lead. And common because you've got lots of stuff at 0 volts typically in a circuit. So on this wheel, you see there's hard to read in green, but that V with a straight line across, that's direct current voltage. So VDC, VAC with the sine wave, the omega for ohms, that's your resistance, and then other stuff, amperage, and there's also frequency. On resistance, one of the useful things is that at a very low resistance, there's a audio symbol, and that's going to give you a sound when you have connectivity. You know, when you're at the same node or same equipotential, like if you're touching two wires, two sides of a wire, it's going to say you have connectivity through that wire. So the first thing we're going to do today is provide 24 volts to each of these three lights. And we've got the lights here. I'd like you to draw this. 24 volts is going to come out of this box. So that's this symbol, and then each light looks like that. So go ahead and draw 24 volts going to each of these lights. Each light needs 24 volts. All right, so we wired up 2 because 3 in parallel is the same deal. Well done, they're working. And I'm going to unplug this so you can handle the wire safely. But if you want to just hold that up, you can see we went with a terminal block this time. So we've got the 24 coming into one side, 0 going into the other side, and then that whole top is going to be at 0 and the whole bottom is going to be at 24. And what advantage that gives you over another way of wiring it, called daisy chaining, is if you do this jumping between terminals like that, then I can pull out this wire and lose power down the chain. Whereas here you can pull out a wire and the other stuff is going to be okay. Alright, so next circuit we're going to make is one with a single switch like this, a double switch, and these are connected, which means if one switch closes, the other switch is closing at the same time, and a motor. And you've already messed with terminals, but a terminal block is going to come in useful here also. Terminal is just the termination of a circuit, so where a wire comes in and terminates into a connector. And it's worth explaining why I've shown this as outlet as a switch. So the way to think about this is that on the left side of the switch over here, that's this part, and on the right side of the switch is this part. So I said if one switch closes, the other has to close, and that's because physically this thing has these two connections on it, and when you push it in, actually it has three, and when you push it in, all three of those switches are closing. So that's how this is a switch. And if you'd like, you can build this circuit once you've drawn it up, because we're going to build it next. You can build this with an e-stop, and that's doing the exact same thing. When you push on the e-stop, what you're doing is pulling a plug out of the wall. Essentially, you're opening up, we've got two connectors here, you're opening up two separate switches. You're opening up two switches. And when you reset the e-stop, you're making those connections again and allowing current to flow. So go ahead and draw up this circuit, please. All right, so that's the circuit. That's what we have wired up also. We've got this motor mount, which is patent pending, R&D leverage. Can you hold up the switch? Okay, then go ahead and hit the switch. There you go. Okay. Last, I'll say, go ahead and hold that up again. I'm going to unplug it now, and now hit the switch again. So it's a good thing to keep in mind is when you're working with any sort of electrical system, there could be charge stored up, often stored in the capacitors. So just because it's unplugged doesn't mean that it's free of charge. Yeah. It was stored in the power supply, correct? Yep. So we use the multimeter in various places. We use the multimeter to see when the switch was on or off. We used it to find connectivity between the inside portion of the outlet and what's coming out of the end of the cable. Next, we're going to move over to Breadboard, and we've got one sitting here. It's the exact circuit that you see pictured there. Something to understand here is that there's rails or planes or buses, and those words are referring to equipotentials. So it's useful to have 24 volts in several places in your system. So instead of doing a daisy chain, you would want like a strip of 24 volts, and then things just plug into that, and you know they're getting their voltage requirements. Here we've got 5 volts coming out of that red terminal and landing here, and 0 volts coming out of there and landing here. Internally on the breadboard, this whole row, I'm talking about just the top row of sockets here, this whole row is connected internally, so that's one contact point. It's the same deal with here. Just below it is all connected to each other. And they're labeled as such. That's minus. Because I connected the minus to it, we know that that's minus 0 volts. And that is going to be 5 volts. We take both of those connections and bring them down here, and now we have a rail going all the way down there for 5 volts and for 0 volts. That's connected internally. Outside of those rails, we've got these sets of 5 sockets all over the breadboard, like here, 1, 2, 3, 4, 5. Those 5 are connected internally, which means that if you take wire A and plug it in there, take wire B and plug it in here, you've now made a connection between wire A and wire B. And it's just those 5. It does not jump across to the other side of the row. Right now, these aren't connected to anything because you can see there's nothing jumping over to the power source. All right, so for our circuits that we're working with today, we can take it for granted that we've got 5 volts on the left rail here next to red, and we've got 0 volts on the right rail next to blue. The first circuit we're going to do is here, lower on the breadboard. It's pictured right here, and I would like you to draw that circuit, and then we'll discuss it. Okay, so we're drawing this circuit. That's what the circuit looks like as it was wired up. And the problem is that these two are not connected to each other. That's why it's an open circuit. So if you wanted to fix that, you would make that connection. So you want to go ahead and do that? Well, let's show it first. So there it is. Light is off, no connection.
So these just push in?
Yeah,
wire?
you can just pull that out. So that's out.
Connected 35.
Yep, connected to 35. Now we switch it on. The circuit is on. Using that same circuit, if we wanted to add a single wire to short out the LED, where would we add that wire?
To short it out.
Yeah. So we're going to put a wire in such a position where it's much easier for the charge to flow through that wire than through the LED.
So you're going to jump between 35 and this black wire. From here.
Right.
Here.
Yep. Yeah, can you show me on the diagram, actually? We've got your diagram here. So that was closed.
We closed it.
Yep.
So we're going to jump here.
Exactly. Yep. So you got a wire going from between the resistor and the LED down to the minus. And we got a wire here.
Do it.
Yep, let's go for it. Bingo. Yep, lights off. And if we pull out that short, you want to pull out the short now? And back on. There you go. Okay. So this is our next circuit. Let's take some time to kind of understand how this rat's nest of wiring matches up to the pretty diagram that we have. And our goal is to figure out what element we can pull out of the circuit to shut it off. And if you're looking at just this area of the circuit, so assume that it gets its 5 volts and its 0 volts here. There's only one element that we should be able to pull out and actually shut off the LED. So let's take some time to understand it. Okay, so we identified this resistor here as being this resistor in the diagram. And if you pull it out, go ahead. That one. The LED goes off. So what happens when that resistor is removed from the circuit is that there's no way for the current to get all the way from the positive terminal to the negative terminal, therefore current is 0. And the reason we could pull out pretty much any other element on there is because all these resistors are actually shorted. So when you've got 5 volts here, that 5 volts is actually all the way through this node and completely shorting out that resistor. And it's the same thing going on here and here. The current just passes almost entirely right by the resistors. And that's the last of this class. So we'll start in on industrial electrical components next time.